A segment tree is a data structure that stores an array and supports two operations: range query, given a range left to right, return the sum, min, or max of elements in that range, and point update, change the value at an index. We store the tree in an array with 1 based node indices, the root is at index 1, and children are at 2 times I and 2 times I plus 1. Your input array can stay 0-based in code, only the tree indexing is 1-based. Both operations take logarithmic time. We build the tree once in linear time. Segment trees are used for range sum or range min queries with updates. For more advanced cases we can add lazy propagation. A segment tree is built entirely on the principle of divide and conquer. We start with our full array of raw data, representing the range from index 0 to 7. We find the midpoint and chop it exactly in half to create a left segment and a right segment. We repeat this slicing process recursively, chopping each block in half again. We keep going until every single element is completely isolated. If we organize these segments vertically, a perfectly balanced binary tree emerges. The leaf nodes at the very bottom hold the individual raw elements from our input data. Every internal node sitting above them holds a specific segment, representing the combined responsibility of all the leaves buried underneath it. Even though we visualize this structure as a branching tree, we store it inside a simple, flat array using a strict math rule. We place the root node at index 1. From there, any parent node at index I automatically maps its left child to index 2 times I, and its right child to 2 times I plus 1. The next tier maps into the array the same way. This geometric layout lets our code jump up and down the hierarchy using fast arithmetic instead of pointers. Now let's see how our tree answers a range query. Suppose we want to find the sum of all elements between index 2 and index 6. Instead of looping through those 5 elements manually, our query engine drops onto the root node and checks how its pre-calculated segments overlap with our target. Overlap means 2 index ranges share at least one position. Our query wants indices 2 through 6, while the root node represents 0 through 7. They share 2 through 6, but the node also covers 0, 1, and 7, indices our query does not need. When ranges overlap only partly like this, we call it a partial overlap. The engine cannot use the pre-calculated sum of the whole node. Instead, it splits its search path, sending one probe down to the left child and one probe to the right child. Let's trace the left path first. Node 0 to 3 is another partial overlap, so we drill down further. Its left child, range 0 to 1, has 0 overlap with our target of 2 to 6. The engine drops it instantly, returning a value of 0. However, its right child, range 2 to 3, is completely inside our target query. This is a complete overlap. We stop drilling, harvest its pre-calculated value of 3, and safely return up the tree. Now, our right path executes the exact same logic. Node 4 to 7 splits. Its left child, range 4 to 5, is a complete overlap, allowing us to harvest its entire pre-calculated sum of 13 in a single step. Its right child splits once more to separate index 6 from index 7. We ignore 7, grab 6's value of 3, and our search is done. The engine rolls these values up, 3 plus 13 plus 3 gives us our final answer of 19, achieved by checking just a tiny fraction of the tree. Now let's see how a segment tree modifies its data. Suppose we change the value at index 4 from 4 to 10. Because this is an interconnected tree structure, we can't just change the leaf in isolation. We must execute a precise top-down search to find this exact leaf, modify it, and then rebuild only the specific parent nodes affected by the shift. We initiate our update at the root. Instead of splitting this time, our engine performs a highly efficient binary search. It checks the midpoint of the root's range. Since index 4 lives in the right half of the array, the left half of our tree instantly shuts down. The engine races down to the right, continually having its options until it isolates the exact subsegment containing our target. The search terminates the moment we hit our base case, a leaf node where the left boundary equals the right boundary. The engine updates the leaf instantly, swapping out the old value for our new value of 10. With the foundation updated, the engine now reverses direction to fix the path above. As the function call unrolls and climbs back up the tree, every parent node along the search path recalculates itself by adding its two children together. Node 4 to 5 updates to 19. Node 4 to 7 updates to 29. Finally, the root absorbs the change, updating the global total to 45. Because our engine only touched nodes sitting directly on our search path, this update is completed in perfect logarithmic time. Let n be the length of the input array. Building the tree is order n, we visit each node once in a bottom-up pass, about 2n-1 nodes total. Range query and point update are order log n, the query splits at most 2 ways per level, and the update follows one path down to a leaf and ripples back up. Space is order n for the tree array, about 4n slots when n is padded to the next power of 2. Here is the pseudocode for the 3 routines we walked through: build, range sum query, and point update. Build copies the input array into the leaf band of the tree, then merges bottom up, each internal node stores the sum of its two children. Range sum calls a helper at the root. Complete overlap returns the stored segment sum. No overlap returns 0. Partial overlap splits to the left and right child and adds the two answers. Point update descends with binary search on the segment midpoint until it hits a leaf, writes the new value, then recomputes every ancestor on the way back up.